Okay, so recording. Caleb has a presentation for us. I met Caleb because he was tutoring me in physics and then also some calc. And we met at Penn State. And right now he's at Penn State doing graduate research. So Caleb, take it away. Thank you for your time.
Yeah, absolutely. Hello, everybody. I will see if I can maneuver this, share my screen, and begin a slideshow. You guys can see that? And is it the correct screen? You see it, mathematics and engineering, not the notes. Yep. Cool. All right. Hello, everybody. As discussed, my name is Caleb Thompson. I am currently a master's research assistant here at Penn State University Park. I earned my bachelor's in materials engineering with a minor in math back in spring of 2022. Currently pursuing a master's degree in mechanical engineering, again, here at University Park, doing research focused on heat transfer and two-phase heat transfer. So to start, just a quick game plan for what I'm going to cover in this presentation. So I want to talk about the types of math that I use and have used and want to use in either graduate work or otherwise. So my first example I'm going to give you will be an ordinary differential equation example. Who all here is familiar with differential equations? Just give a thumbs up or a hand wave or something. Okay, so a couple. So we'll talk about differential equations. We'll talk about partial differential equations, which is like the ordinary differential equations, bigger, meaner brother. And finally, I want to give an example of pure math, which some of you might have seen in discrete math. I don't know if you'd have gotten there yet. I know our class hasn't, but we'll talk about the proof that the square root of 2 is irrational. So first, I want to talk about the ordinary differential equation modeling of COVID-19. Before we even talk about the modeling, though, we need to answer the question of what is an ordinary differential equation. The answer to that is it's any equation that contains a function and its derivatives. So here is a super basic, like first day example of what an ordinary differential equation can look like. F prime of x equals f of x. So all this is saying is that a function is given such that the function is its own derivative. Now, if anyone familiar with calculus might be thinking, okay, well, function who is its own derivative, I might know what that is. But you can prove this pretty rigorously. So the first thing is you break it into the Leibniz notation for the function. Then you treat those differential operators that aren't fractions as if they're fractions and break all the rules and set it up like this. Well, now you just integrate that and you get your answer. So you find your natural log of the function is x plus c, do a little algebra, and you find that the answer is c e to the x. Here by log rules, e to the x plus c is just the same thing as a constant times e to the x. Those aren't necessarily the same constant, by the way, that c and that c, because you can break e to the c plus e to the x plus c into e to the x times e to the c, but that constant's arbitrary, so we left the name the same for convention. So there's real quick overview of what a differential equation is, what it does. Next, so this is a particular differential equation that's used to model population growth. It says p prime equals alpha p times 1 minus p over m, where p is, well, we'll start with p. P is the population. So this can be number of fish in a pond, or number of bacteria on a swath, or number of people in Illinois. Any of those, any population. M is what we call the carrying capacity of the environment. So if you think of a pond that can hold 500 fish, okay, so that is M equals 500. And you can see the second term, if your population approaches your capacity, so say we have 300 fish, then 400. As P approaches M, as your population approaches the capacity, this term approaches 0. Because of that, your growth slows down. You get fewer new members of your population. P prime is the change in population over time. So that's like dp dt. So what this equation really says, if you squint your eyes, and we'll talk about alpha, alpha is like propagation or spread rate. So higher for, fish that have a lot of baby fish, lower for fish that don't. So if you really just kind of zoom out on this equation and think about what it says in general, it says the number of new members of your population is proportional to how many members you had yesterday, as well as how many members your environment can hold. So that's what's cool about differential equations, is that's a really basic concept. And it yields some really complicated answers. So I don't have the analytical solution to this one, but here's some plots. If you set alpha to be 1/4 and m to be 500, then this is what your plots look like. So after, if your initial condition is that there's 200 fish, then it follows this curve, right? If your initial condition is that there's 70 or so fish, it follows this curve, and all kind of level out at that 500 capacity. That's another important aspect of differential equations, is you have to have a starting point, an initial condition. So in this case, the initial condition is how many fish you have on day one. Now, this population model, this was back in 2020 when COVID was kind of top of everyone's mind. I worked with a professor at Du Bois who's had done research himself on this logistic model, and we modified the logistic model. So we said that P double prime was the increase in number of new COVID cases per day, which makes P prime the number of new cases per day. We basically just moved the derivative order up by 1. So P prime is the number of new cases per day. P double prime is the change in new cases per day, basically. So there's 17 more new cases than there were yesterday, is what P prime would represent, or P double prime. M of t and alpha t are two time-dependent functions, basically. So we said that what happens if you limit the amount of new people that COVID can infect? So that's M of t. Alpha t is what if you do something that changes the spread rate? For example, you put more people in small buildings in the winter, or more people wash their hands more often or touch their face less, or the virus mutates. Any of 1,000 different things. Alpha would be what we call in engineering a fudge factor, which means there's 100 things that affect it and nobody can figure out exactly what they are. So you slap a number on and see if it works. And that's what we did. I did curve fitting for this. But because we have time-dependent, piecewise defined functions here in our differential equation, it would be really impractical to do that process we showed earlier of separating and solving. It's just would be impractical for any analytical solution. So our solution is something called Euler's method. What Euler's method does is it's a numerical method to approximate the solution. We don't know exactly what it is, but we can get as close as we want by using this process. So first, you set delta t to be some finite change in time. For this model, we used 1 day. And then your equation becomes f of t. So your value of the function at a given time is roughly equal to the function at the previous time step plus the size of the time step times your differential, the slope at that point. This is also known as the forward difference method. Anybody here know Taylor series? A couple people. Yeah. So this is, if you look at this, this is exactly a Taylor series truncated to the first order. And it's used in this process. It's not exactly a Taylor series, but that's the point. So to describe a little more what's going on here, you know your function at this point. And so the approximation says, well, assume that in this distance, this delta t, this dt, that's inconsistent, assume that it's linear. This is the same thing done in differential calculus, except there dt is not finite, it's infinitesimal, it approaches 0. But here our function would just approximate, okay, take the slope here. Well, in that case, assume the value of the function is going to be somewhere around here, where that blue line intersects the second black dotted line. So you can see it's not super accurate, but on parts of the graph where it's more linear, it's more accurate. So the result we got was a semi-neat plot. There's a lot going on here. This was for the first about year and a half of the COVID testing results. So you can see the black line here is our real data. Well, real data. It's what we were able to find from the CDC and load into MATLAB. So we have the pink, which is our capacity function, and finally blue, which is the model data, which again, the functions for M and T were super complicated and piecewise. I mean, you can see M, it starts linear, then here we did a little bit of a quadratic-ish slope, jumps up here, linear slope down here, linear slope, changes, sharp corners all over the place. Awful. But our function, since we took a step at a time, linearized it, we don't have the exact answer. We don't know what that is. But we were able to get a function that smoothly approximates what the answer probably looks like. And there's a couple different important points marked on here. You can see where the lockdown starts. You don't see an immediate change. There's some drop off in the summer. Alpha drops a little bit, the spread rate decreases, and so does the capacity. You get back into fall, you see it jump back up, kind of tapered off a little bit, then really jumped up again in the winter. When the first vaccination was released, you did see a significant drop, but that also coincided with the spring, which, as I discussed, was people getting back outside, less enclosed spaces, fewer people in school. So there was a lot going on here. We didn't really get any solid answers out of it. It wasn't a predictive model. It was a prescriptive model. It was saying, okay, here's what already happened, so maybe this is what's going on. But this was a good application of an ordinary differential equation that we couldn't answer directly, but used a numerical method to do so. The next one is something called partial differential equations. So here we modeled heat transfer. This was in my graduate studies last semester. This was just for a class. It was a final project, but it still turned out pretty cool. So we talked about what is a ordinary differential equation. A partial differential equation is very similar. So this is an example of one. It is a multivariate function and it's multivariate derivatives. So here, just for an example, I have derivative of f with respect to x and the derivative of f with respect to t combined equals some function of x and t. Has anybody here seen a partial differential equation before? Okay, couple people. Partial differential equations are, like I said, like the ODE's older brother, and they're a lot meaner and don't respond well if you try to solve them. They're very, very difficult. So for an example, here is what's called the heat equation. What this says is, this describes how temperature changes across a surface, specifically via conduction in this case. But you can see you've got a second derivative of conductivity, which is how heat transfers through a plane material, times temperature. This is a heat generation term. And then you have a time differential here on the right-hand side. So this is a partial differential equation with 3 different independent variables and 1 dependent variable, that t, one function we care about. And this on its own, this is actually one of the very simplest differential equations, does not have any solution that I'm aware of. I've never seen someone who could solve this in 3. I'm sure it can be done. I'm an engineer, unfortunately, not a mathematician, but the point is they're very hard. So a very simple example is what's called this 2D steady state conduction equation. So you take a lot of the terms in that big mean equation and you say, okay, there's 0, which is almost never possible, but we did it anyway because it was a class. So this the question here is, okay, if you take a rectangle where one side is 100 degrees Kelvin, the other side is also 100 degrees Kelvin, and the top is 300 Kelvin, and the left is 200 Kelvin, what is the final temperature distribution? What's it look like? So that is this governing equation here. This one is solvable analytically. Oh, my animation didn't work. So there's the analytical solution. So what you do is you break the problem into two problems, adding them using the principle of superposition, where the sum of solutions must also be a solution. A non-homogeneity, NH, is a wall temperature that isn't zero. So you split it up, you do all kinds of manipulations to it. You can solve each of those via a process called separation of variables within partial differential equations, and then use a process called orthogonality, which I don't totally understand. I used it a whole lot last semester, but it yields something like this. By something like, I mean exactly this. So there, that is your exact solution. That is exactly what the temperature is for any x and y. All you got to do is plug it into this equation. It's beautiful, isn't it? The only problem is you do have an infinite sum here. Computers, pro tip, aren't good at that. They can only sum a finite amount. And my computer broke when you got to the hyperbolic sine of 711. Anything higher than that, and it said it was infinity. So not actually very accurate for being an exact solution. So this exactly describes what's going on, but unfortunately we can't use it very well. Well, at least I couldn't. So the next solution is a numerical method. So this is called the central difference method. And it does the same process that we did for Euler's method. I think this is actually classified as one of Euler's methods. I'm not certain though. So again, we're dealing with a derivative, some discrete step in x and y, delta x and delta y, and the temperature at 3 different nodes. So basically, if I say, okay, here's your middle node, then you're going to check the temperature before it, the temperature after it, and then you know the temperature in the middle is what you're trying to find. You do the same thing in the up and down. Delta x equals delta y is an assumption that you can make since I programmed it. I decided delta x should equal delta y. So then this is a lot nicer. This is what's called a convex average, and saying that center temperature Tij is what we want to know. So we're basically averaging all the other temperatures around it. It's what's called second order accurate. So the truncation error is of the order of delta x squared. So as delta x decreases, the error decreases as the square of delta x. So it's pretty accurate. Of course, you still have an error. That truncation error still exists. So here is the result of that. This is a GIF that I made in MATLAB of how the temperature changes over time. Depending on your, well, the time it takes to do this is arbitrary, but eventually you see that that cold front kind of moves in from the side, the hot side comes down, and eventually collapses. So that was a cool result, I thought. But again, we have that truncation error. It's not exactly right. We've used a numerical method to approximate the solution. So the final example that I want to give is from pure mathematics. This is the proof that the square root of 2 is irrational. And I just think it's neat. So this is what's called a proof by contradiction. So what we're going to do is say, okay, assume that what we want to prove is false. So assume that the square root of 2 is rational. Now, to talk a little bit higher, a rational number is any number where you can write it as a fraction that can't be reduced. So this would mean the square root of 2 equals a over b, where a and b are whatever numbers the square root of 2 would correspond to. So, for example, 3 over 15 can't be reduced. 5 over 15 can be reduced because they share a common factor. So we assume first that this is true, that a over b can't be reduced, and that square root of 2 is rational. So then you follow through the implications for that. Well, in that case, when you square both sides, you find that 2 equals a squared over b squared, right? Simple algebra. Following this through, multiplying both sides by b squared, we find 2b squared equals a squared. Nothing too fancy yet. We know the square root or the square root of an even number, if it's rational, is even. Saying that forwards, an even number squared is always even, an odd number squared is always odd. So from this, we can conclude that a must be even. Cool, we've actually narrowed something down. But then if a is even, we can write it in terms of 2 times some other constant, which might be even or odd. It doesn't matter what c is. So if a equals 2c, well, let's follow this through logically. So a equals 2c. This implies that a squared is 2c squared, or 4 times c squared. But here's where our problem comes in. We said earlier that 2 times b squared equals a squared, right? But in that case, we know a squared is 4 times c squared. Divide through by 2, and you find that b squared equals 2 times c squared. Well, 2 times any number is even, assuming it's an integer number. So that means b must be even. Now here's our problem. If a and b are both even, then a over b can be reduced, and we've invalidated our proof, which means the square root of 2 can't be expressed as a over b in a way that can't be reduced. So square root of 2 is irrational. I'm pretty sure they killed Pythagoras for that. But personally, this is, of all the things that I've talked about, this is the coolest. There's no fancy graphics, there's no pictures. A computer was not involved in any way. This was back when computers were the people who sat down and computed things. But this is something that you can carry in your head. You can go and write this down. There's no graphics, there's no computers. It's something true. We didn't make any approximations here. We have no truncation error. The square root of 2 is irrational. Proven. So this leads me to kind of a question. Which is better, pure math or approximate solutions? On the left-hand side, that's the Mandelbrot set. Some of you are maybe familiar with it. Really cool theoretical thing that I definitely don't fully understand, but it's neat. On the right-hand side, this is actually a picture from my current research. So this is buoyancy-induced flow in a curved surface or on a pipe. So as water warms up, it expands a little bit, and since it's expanded, it's a little lighter, so it floats. So the question we're trying to answer is, okay, as that water floats along the side, how does it flow? So this image was generated over the course of several hours using a program called StarCCM+, a fluid dynamics, computational fluid dynamics solver that took those linear approximations we talked about earlier, did them millions and millions and millions of times on thousands of points, and gave that pretty looking thing. But to answer my question of which is better, that's an approximate solution. Left hand is pure math. Right hand side, we're using to figure out how heat moves in a pipe. Left hand side, I don't know what you use that for. So the answer to this question is, what do you want? Do you want answers or do you want solutions? And let me explain the difference to this. So say you have a locked door in front of you with a padlock. So if you ask someone, how do I get into this room? The answer is 7496 pinned to the padlock. So that's what a mathematician gives you, is an answer. The engineer pulls out a fire axe and breaks down the door. Engineer could care less what the truth is in something, but they just need to solve. They have a problem, they need it solved. So mathematician gives answers, an engineer gives solutions. To illustrate this, here's a meme that I stole off the internet. Corporate needs to find the difference between these two pictures. They're the same picture. Pi equals 3. It's close enough in way too much stuff. Actually, 22/7 is what engineers would really say, but it works. And on the flip side, this is worthless, which is technically probably true. But I personally, I think that's part of what makes pure math a lot more interesting. It's more of an art than engineering by a lot. But that is all I had. So thank you. And here's just as Mabel brought Zoom to see me out. But any questions?
Okay, well, first of all, thank you so much for that presentation. It was very entertaining and I think gives like a good glimpse into what you do as a grad student. So if anyone has any questions, they can just put them in the chat or say them out loud. Otherwise, I have some like guiding questions that we can use. But yeah, speak now.
Hi, can you hear me all right?
Yeah, I can. Who's-
Awesome. Daniel Chappell, Hi there.
Okay. Oh, hi, Daniel.
Hi. I've never heard of a graduate in mechanical engineering. Except for you.
Okay.
I guess that might be because I live here in the Valley, and so it's all electrical engineers.
Yeah, well, yeah.
Yeah. But I'm wondering then, what are these mechanics you're studying? You talked about heat flow and fluid flow. Could you elaborate?
Sure. So mechanical engineering deals, as the name implies, with mechanics, with how basically how anything moves. So it can be energy, fluid, material, heat. My focus is in heat. So there are anything from the quantum level, nanoscale heat transfer across micro tiny particles to what I'm doing, which is a big old pipe. That is one facet of mechanical engineering. I've only been in mechanical engineering for about 6 months now, but that is the best description I can give. Is it deals with motion of whatever you're talking about. So other stuff in mechanical engineering that you can get into is something called system controls, I think. So that's, for example, I've never had a systems controls class, but you're trying to build a power plant, okay? And you want to make sure that the power plant stays running. So that's what that side would be, if I'm correct. But yeah, in a broad sense, that's what mechanical engineering is.
Thanks. Okay, so to
yeah.
clarify, mechanics would generally be the study of how something moves, some sort of motion. And then the engineering is just engineering that, getting the axe, right?
Exactly. Yeah.
All right.
Yep.
Thank you so much. Thanks for presenting,
welcome.
and
Thanks
thank you for organizing this, all of you organized it. Thanks.
Does anyone else have any questions? Guys, you got like a person who did stuff with math. Like this is math club. Feel free to ask him any questions. He's here for like the next 20 minutes. So yeah, if no one else has any questions, I do have some, but I'll leave it open for a bit.
I think earlier you said something like the proof that square root of 2 is irrational was why Pythagoras was killed, right? I thought it was something like him running through a bean field or something. And then
I don't actually know that. I'm not certain. Yeah, I don't know. Could be. I know the ancient Greeks weren't happy when someone told them they couldn't write down a number. Irrational numbers were a big controversy, but yeah, I don't know if that's actually what he was killed for. And anything else? Something else I didn't talk about that I really like is infinite series. So if you add up infinite numbers, you can actually get a finite result. So 1 over 1 squared plus 2 squared plus 3 squared plus 4 squared, or 1 over 4 squared, 1 over 3 squared, etc. Adds up to 2, which is just goofy.
Oh, have you seen the one where it's like
negative 112?
Yeah. How did
That one's silly because the way they present it is not quite right.
Yeah.
It's technically a little bit more subtle than saying adding all those numbers is -112.
Is that
n-
useful at all, or is that just like a little quirk they found?
So you ever watch Number File?
Yeah, that's where I saw it originally.
Yeah. There's one guy who does, there's a physicist guy who does it, and he's fine. Actually, I will stop sharing. Right? So I can cheat and look this up. The physicist who does it is fine, but he makes it seem a little more mysterious than I think it is. So there's a guy who describes it as a gold nugget. The physicist guy talks about it's used all over the place in even like airplane construction and stuff. So yes, the -112 result is useful, even if it's not exactly like true. So short answer, yes, sorry.
Yeah, we worked with, in the club meeting recently, we worked with an infinite product that Sakith brought up. It was this problem. And there were two ways you could do it. Sakith did it by equating x equals this product and then cubing both sides and then replacing what would go here because the cube gets taken away with x, and then it would be x cubed equals 10 to the 1/3 x. Wait. No, it would be, sorry, 10 to the 10x, and then you could like solve for it that way. But another way that our advisor showed us how to do it is doing 10 to the 1/3, like 3n to the n power, and then using that infinite series and saying that because it's a geometric series, it converges. And then we
Right.
found that converges to 1/2. And so you get the same answer with both of them. So I just thought that was
Cool. That is cool.
Yeah.
Yeah, I definitely would have taken the series route if I, yeah, because that's where I prefer.
Okay, if no one else has any questions, I do have some that I think everyone could benefit from. So, in terms of opportunities, I know that you told me before this call that you wanted to have a master's in math instead, and then you were offered this opportunity. How did you get that opportunity? Do you feel like you still want to go the math route at some point, or you're happy with where you landed?
Yeah, so for those of you who are just now meeting me, which is almost all of you, my undergrad was in engineering, and my sophomore year, I very nearly switched to math because I did an engineering internship, found out how little math actually gets used by real engineers as opposed to those in academia. And I said, I really think I want to stick with, I got into it because I liked math. And if I'm not doing math, why am I here? Ultimately, I stayed in engineering and I applied for graduate school for math. The 3 different schools, all 3, well, one didn't even respond, one rejected me outright, and one put me on a waiting list and then later rejected me. So that was fun. And I had so my plan then was to go on for another year of school and take a double major in math, which was going to be expensive and not that much fun, but to try and get into graduate school for math. I had a friend who was talking to a professor. That professor knew a professor here at State College who was researching and had the opposite problem most people have, where instead of having people and needing money, he had money and needed a person. And I was told he was desperate, and I said, hey, sounds like someone who would take me. So that's how I got put here. I almost said stuck here. So kind of friend of a friend. While I'm here, I'm taking as many math classes as I can. I'm auditing discrete math right now because I couldn't get it at Du Bois where my branch campus was, and I can't take it as a graduate student. So I'm just sitting and watching. I'm doing everything I can to try to get back to math. So I described earlier, engineering is the one that takes the fire axe to break the door down. Mathematics is the one that figures out, why the door is locked, where's the key. I think those are much more interesting problems. I really like pure math. I think math is a form of poetry. Actually, I'm reading a book right now from 1962 called Mathematics and Poetry, or Poetry and Mathematics. I'm reading it the right way. Math is a tool to explore truth in the world. Same thing as poetry is the thesis of that book. But engineering doesn't care about what the true thing is. We say, I don't care exactly what that is. All I need to know is, is it close enough? And maybe I shouldn't be saying this in front of all you potential engineers. Go be engineers. You make lots of money. But I just don't have, my passion isn't for close enough stuff. I want to know exactly what's true. So that's why I'm going to stick with math. So my plan after this is to try to get into a math PhD program somewhere with a master's in mechanical engineering. I'm closer, but yeah.
Cool. In terms of opportunities, like the engineering internship you got, so for you guys who don't know, Penn State has like 20 branch campuses. So most of them are smaller. And so the one that Caleb's at right now is University Park, and that's the main one with like around 40,000 undergrad. So the engineering internship, I haven't heard much about it. Did you acquire that through Du Bois, through your, connections? Like, how did that?
Yeah, so that was back at Du Bois. That was my first summer after, so I was a freshman, came out of my freshman year and applied, just sent out cold calls, sent out letters and resumes to people all over the area. That was in something called powdered metal, which is really big in our area. And only one responded, and it was a place called Simcoe in basically my hometown. So there was someone, so I think at most colleges you're going to have someone in career services. So I went and talked to her, and she said, oh yeah, apply here, here, and here. We've done internships with these guys. Here's how you want to present it. And none of the people who she suggested responded. And I was like, I know this place. I could try that. And she's like, yeah, sure, go ahead. And then I did and got a job there. I think they felt bad because they just stuck me in the back room where I measured parts all day, every day. And they screwed up. So I measured parts. I measured one set of parts like 3 times, which was awesome. It was this. This is a hospital break, or a break for a hospital bed. They gave me one because I spent my whole summer with them. That's on my keychain. My keychain's pretty heavy. But so yeah, so that's how I got into that. Was I just literally basically just cold called, but with emails. It was a good opportunity. I got to see a lot of the industry, and that I wasn't a fan.
Cool. Talk to me about MATLAB and coding in your engineering process. Do you like it? Do you hate it? And like, how does it integrate with math as well?
Okay, that's a good question. So MATLAB, I've described as it's the equivalent of owning an ugly dog, right? Like, it's not good. You know it's not good. Everyone around you has something better, but you love it anyway. That's how I feel about MATLAB, because it was the first programming language I really learned. So far, the only one I really know. And so it doesn't have 0 indexing, right? So the first term in your array is 1, which breaks so much stuff. I didn't realize it was bad until I tried to do other stuff. Indexing and function calling are the exact same thing. It's both with parentheses. It's bad, but I love it. it's got a butt ton of built-in functions and stuff. It's got an included differential equation solver, DSolve. Like you're not going to get that in, well, you might get that in Python and Java, but so that's one of the reasons I really like it. It's good at graphing. That GIF I made was in MATLAB. MATLAB's a lot of fun. I like it. But as far as how that applies to mathematics, we were talking a little bit beforehand about you're doing logic now in discrete math. I am also in a discrete math course talking about logic. The way that you describe a continuous function in discrete math is very rigorous and very obscure at first. When you realize what it's doing, it makes a little more sense. That is with if-else statements in any programming language. If you are good at constructing logical statements like that, you can do anything with an if-else ladder. So that is an area where pure math is super helpful in programming. Logical pure math, not so much the Mandelbrot set, stuff like that. But being a good mathematician will make you a better programmer and vice versa. Or so I say.
Does anyone have any other questions for Caleb? Then one thing I do want to ask, since you're in a Zoom room full of like undergrad, mostly STEM students, I don't think anyone here is like either they're undecided or a STEM major. What advice you would have for them?
So my best piece of advice is on the problem solving side of things. And so I tutored physics and math and still on occasion tutor physics. So the problem solving strategy, and you'll have professors tell you this too, is always take what you know, what you want to know, and try to bridge that gap using equations you've learned or other relationships. So, if I give you a car at the top of a hill with friction coefficient and gravity and mass and tell you, okay, how fast is it going at the bottom of the hill? So you take what you know, those options, what you want to know, and your goal is to bridge that gap. You'd use kinematic equations, stuff like that. It's probably not it's very, very pragmatic advice when maybe something more philosophical would have been appropriate, but that is, yeah.
Yeah. Do you have any, since you are reading like a book about math, do you have any like book or movie or website recommendations for those who want to get more into math?
Yeah. So Numberphile I talked about is a big one. There's Matt Parker, who's on Numberphile. I watch him a lot. XKCD is a web comic by a physicist named Randall Monroe. That's a really fun one. The longer I'm an engineer, the more of his jokes I get, and that's just funny. This book is called Poetry and Mathematics, written in 1962 by a guy called Scott Buchanan, and half of it is just him fighting with other mathematicians from 1962. I don't recommend it. It's interesting. It's very philosophical. It talks about connections in math and poetry, how analogies connect, how ratios are actually something that exists in plays, in literature. It's intellectually interesting, but I'm not going to say go read it. Actually, I might even find the link to this. A Mathematician's Lament. This is, anybody ever hear that? Also
Yeah,
called
so when you recommended
Yeah,
it to me, I read like maybe like 15 pages, and I didn't read the whole thing though.
That's fine.
You
Yeah.
can explain what it is.
So also called Lockhart's Lament. It is a description of math as an art and how it's been taught wrong in everywhere. It's the equivalent of teaching kindergartners to read by making them fill out tax forms, having them drill times tables and stuff like that. It's backwards. And that's why so many people who would be good at math, would love math, feel like they hate it. And it is really sad and makes me want to go learn to teach math, which is kind of the end goal here. Oh, this is the MAA, Mathematicians of America, which is actually where I presented the COVID research back in 21. But there's a link for it, Lockhart's Lament. 10 out of 10, would recommend that.
Yeah, I want to read some quotes from the paper. Basically, it starts off with how we view music as like an art, but not math as an art, because it's seen as something that has like practical application, right? But the way we are taught it is like basically pure math, right? Like it's not really applied math anyways, so people don't see it as something that can be applied to real life. So the first part is about how a musician is put in the position of a mathematician. So as for primary and secondary schools, their mission is to train students to use this language, to jiggle symbols around according to a fixed set of rules. Music class is where we take out our staff paper, our teacher puts some notes on the board, and we copy them or transpose them into a different key. We have to make sure to get the clefs and key signatures right, and our teacher is very picky about making sure we fill in our quarter notes completely. One time we had a chromatic scale problem and I did it right, but the teacher gave me no credit because I had the stems pointing the wrong way. So I feel like that really represents how we're like super picky about the small, or teachers are really picky about the small details, even though what really matters is like the actual understanding. So it's a really great paper and it's available online for free. So I would highly recommend reading that if you feel like there's something wrong with our math education, which there is. So yeah, thank you for the recommendation. So I think we're near the end. So I was wondering if people do want to contact you for more questions, is there somewhere you prefer to be contacted, like your email?
Yeah, so I'll send you guys my email. So psu.edu. There. Yeah, if you ever have any questions about stuff, I'll be happy to help with what I can. I am not a real mathematician. I'm working on it, so I can't guarantee I'll help. And I'm not even a real mechanical engineer. I'm a materials engineer who's faking his mechanical engineerness. That's called imposter syndrome. So, yeah.
Well, thank you so much for your time and your insight. And guys, I'll share this recording once it's done exporting, as well as his contact information, and some of the movies the books that he recommended and the media. But thank you so much for your time. And I hope
Thank you for having me.
it's snowy for the rest of the week. Yeah.
Appreciate it. Thank you very much.
Yeah, thank you guys for coming. Bye.